Okay, well, we have a good collection of people still standing. That's great. And there isn't really a fixed agenda for this last meeting, but it seemed like a good time to follow up on other discussions that had already started. So we could continue some of those if there are important points people want to bring up that they feel should be brought to the attention of the group. Or alternately, if you feel that there's something that we really should have talked about more, this would be a good time to perhaps make some comments on that. So it's, again, fairly open. If we don't have anything to talk about, we can end early. But anyway, let's see if people have things they'd like to bring up.
Give us time to
Process. Yes.
One thing which I think is an important question, which I already have no starting point for, is from this like whole emergent space-time, or at least whole emergent space perspective, how do you decompose Hilbert space into what corresponds to matter and what corresponds to the underlying manifold or space degrees of freedom? Like what kind of characterizes the difference in Hilbert space itself? Things like that, I think.
So separating the gravitational field from the other fields, if in one way of putting it.
Just the classical limit, right? We do think of matter fields living on top of the manifold on the classical. Definitely. So what kind of like leads to that approximation from Hilbert space perspective itself? I agree that...
There's a quantum gravity picture. So why are we asking about what a decomposition looks like? Why are we asking what the decomposition looks like at the classical level? Why do we think that one even exists at the classical level?
It might not be interested with quantum gravity itself, but I think it's like important to ask that under the right circumstances, when you kind of like emerge space and matter, which features of your quantum gravitational Hilbert space kind of map onto these things? Just like with the whole splitting idea or local regions of space even, which might not have a meaningful statement in just like quantum gravitational Hilbert spaces. But like having the right kind of emergence mapping, I think it's...
Maybe one reason why I think it would be important is because if you want to come at it from the other way too, and play the game of starting with classical gravity, defining things like entropies in terms of area, and now look for quantum corrections on top of this. There you very clearly have a separation between what you're calling your geometry and now what you're calling quantum degrees of freedom. And so if you believe that space-time and matter should be really some emergent description from the underlying theory of gravity, well, yeah, you have a description in which space-time and matter is separate in the emergent description, so it better come from there. But I see you disagreeing with me, so...
I think the fact that the generalized entropy is not well defined, either the classical component and the quantum component, they're not well defined independently, but together it's a UV finite quantity. That to me is a litmus, not litmus, it's a smoking gun signal that we should not be talking about them separately.
Is it clear that their sum is always well defined?
Sorry, what was the question?
So you're saying that they add up to something finite?
That's right. Well, I mean, that's the evidence at this point.
Across all types of surfaces?
I believe that at this point this is what has been calculated, but it has not been calculated for all fields. I think that for at least spin 0, spin 1, yeah.
Spin 2?
Not spin 2.
Well, okay. That's the interesting one. Huh?
Well, I mean, I think it's just not understood how to do the calculation. Yeah.
I think in support of Netta's statement, and regarding what you said, this problem of graviton entanglement entropy is probably related to this issue of trying to separate the generalized entropy into some area contribution and some matter contribution, because if you're interested in graviton entanglement entropy, there's probably not a diff invariant way of saying these are my area degrees of freedom and these are my matter degrees of freedom, because from one for one background that could not be well defined compared to some other background. And so finding a way to talk about generalized entropy without decomposing it into degrees of freedom near the entangling surface versus degrees of freedom away from it probably is important for understanding graviton entanglement entropy, I think.
So, of course, there's also the challenge of even defining the entropy associated with a region when you're looking at the full gravitational theory. That's part of the fundamental, sort of a structural problem we have in the full non-perturbative theory that is a big question mark.
I agree. I think this feeds into the same problem of this not being a well-defined question. Yeah, potentially.
Other comments on that thread?
No, just a quick comment, but this is a very trivial, well-known remark that the concept of entropy or information is not well defined. What's the amount of information in the digits of pi? Is it infinite or zero or something in between? And I have the same thing with a black hole. For instance, if I identify the antipodes on the horizon of a black hole, I have a factor 2 problem in my definition of how much entropy there is. So when it comes to having problems with factors of 2 in the entropy, then you can imagine that in physical theories about entanglement, meaning distance or something like that, then you get into all sorts of difficulties in questions as to what exactly does information stand for, what does entropy stand for.
Comments or response?
I think one just has to distinguish between different kinds of entropy. So I think the entropy that people are talking about in Rutakanagi is the information theoretic entropy. So the digits of pi, there's no entropy in them. But you could also talk about a Kolmogorov complexity or things like that, where or if your computer is bounded, you don't have a great computer, then there'll be some entropy associated with that because you won't be able to perfectly predict all the digits of pi, and then there's some entropy there. So you just have to be careful about what kind of entropy you talk about. But I think they're very, the information theoretic entropy is well defined. It's just that when you're talking about pi, you may be talking about some other kind of entropy.
I think the number pi looks like a random number generator to me, because I'm not a mathematician. I'm not.
Right,
but
so
then,
that's how difficult it. If you had a computer that was bounded, how difficult would it be for your computer to figure out what the next digit was? And
yes.
If you have a bad one, then you can't figure it out. So there's some entropy. But if you have a perfectly good computer, then there's no entropy.
Yeah, but there could be many instances in nature where you have this sort of double or not well-defined concept of entropy. You don't know where to start.
Other thoughts or comments? Things that we should have talked more about, etc. I mean, another thing one could ask is, if we truly are after a quantum description, quantum theory of gravity, if that's the goal, what's next? What are the, where should we be going? What questions should we be answering next? Let's keep our eyes on that goal, and how are we going to get there?
So I think one thing which hasn't really been discussed all that much is singularity resolution. Resolution of space-like singularities in particular, and how that happens in quantum gravity. I mean, ultimately, I think that's a question we're going to have to answer to solve the what goes on with black hole evaporation and the information problem. It seems like that's intimately related, and that is a regime of strong quantum gravity. So it seems that we should really be asking questions like, what really happened? That a space-like singularity is a classical gravity approximation of something which is clearly not described by classical gravity.
Most singularities that we know of are censored away. You know, they're behind horizons, and so there may well be formalisms of gravity without any singularities because of that. I like to compare singularities in gravity, even quantum gravity, with singularities in the complex plane. They happen to happen in real space-time, but in domains of space-time that you can't reach behind the horizon. So depending on the coordinate frame you use, there might be real singularities or imaginary or complex singularities, but the number of real singular spaces in space-time that are physically relevant is rather difficult to find.
So a couple comments on that. First of all, we don't have a proof of cosmic censorship, so we don't know that it's true that singularities are going to be always censored away. We don't believe that the initial singularity is not going to be censored away. Cosmic censorship is only formulated for future infinity. And beyond that, the singularities are a prediction of general relativity, which, whether they actually exist in nature or not, has to be modified in quantum gravity. So there's a question of how is that modified, regardless of how is a prediction of classical general relativity modified, regardless of whether that's something that we see. We're not going to see that in nature because it has to be modified in some way, but quantum gravity has to give us an answer as to how classical general relativity is modified in a singularity regime.
So I just have a comment on that. So in canonical quantum gravity, there exist approaches where singularities are actually resolved. So in loop quantum gravity, for instance, or loop quantum cosmology, I mean, whether you like that or not is, of course, up to you. But that's quantization methods, at least in the cosmological sector, removes any cosmological singularities in wherever it has been studied and worked out. So what happens there is basically the energy density remains bounded actually at the Planck scale roughly. So it doesn't diverge actually. Also curvature invariance and so on, they don't blow up. And also if you take expectation values of the volume and so on, they always stay finite. Sorry? Why would that be? No, that's not. So I mean, yeah, no. So I mean, so in those models, there's actually unitary evolution as well. But so there exist also models for singularity resolution in black holes, but they're not quite as well established. In the full theory, it's an open problem because it's technically really challenging. So whether you like, loop quantization or not, up to you. But there's models where that works.
Turned on. Yeah, I just had recently heard a talk by Roberto Emperon about black hole collisions in 6 dimensions, I think. Actually, Maria, are you involved in that? No. Maybe if somebody here is involved in it, they could comment on this. I don't know about it. But the interesting thing is apparently Roberto felt that he had very good evidence that cosmic censorship would be violated in this collision. Not only that, quite shocking to me was that even though it's in 6 space-time dimensions, the problem can be set up with enough symmetry that numerical relativity calculation can be done with equivalent difficulty of a 4-dimensional ordinary non-symmetrical calculation, like binary black holes or something. So that we might actually see, well, then an example where the classical theory is predicting actually a naked singularity in a straightforward physical situation. And it might be interesting, I mean, so the quantum resolution of that singularity might be a more approachable question than the resolution of a space-like singularity inside a black hole because of, well, confusions and lack of knowledge that Herod alluded to and so forth.
Do you want to comment?
Vacuum, yeah. It's kind of a bar instability, I think, induced singularity, if that makes sense, even though it's vacuum, not matter.
So one comment, I'll just make a brief comment and then turn it back. You know, historically, there was a lot of focus on the singularity, but at least sort of my take on that is, well, you can imagine various sort of short distance modifications of the theory, sort of resolving that and smoothing that out and making it regular, maybe, you know, it's sort of effectively highly curved. And okay, so that could just take care of that. But the really profound thing is that somehow whatever information went into that region, you know, doesn't just have to be modified in how it behaves on these very short distance scales, but, you know, it has to make it out to outside the horizon of a big black hole. And that's the profound thing. And, you know, by the time, that's the deep thing. By the time we understand that, maybe the singularity resolution will seem kind of trivial or something. So, or at least that just seems like the bigger problem. So that's my take, I think. But I think the field has also evolved somewhat in that direction in terms of the focus. But anyway, just one comment.
So let me first address Steve's comment, which is that it may be possible that it would be resolving the singularity would actually be illuminating as to the way in which information manages to make it out. So maybe not, but it seems to me that that's part of the problem at least, or maybe part of the problem. Regarding Ted's comment, do you know if Roberto had reason to believe that these solutions, the six-dimensional solutions, actually are reasonable solutions in quantum gravity?
Why wouldn't they be? I mean, they are formed from initial data that's in the classical regime.
But we don't expect that every single classical solution to Einstein's equations admits a UV completion.
Okay, so this six-dimensional general relativity is not, you're asking for embedding it in string theory or something?
Well, I mean, this particular solution may not be embeddable. That's what I'm asking if he has any particular reason to believe that it has to be.
Well, how does okay, the only case I know, I'm wondering what you mean by... Yeah.
I guess it depends on the type of matter that he uses.
But it was a vacuum solution.
It was a vacuum solution.
You have a specialist in the back who's staying quiet.
Do you want to briefly say what it's about, just in a few words?
So, okay, I mean, this is on the line of other known instabilities of black holes that exist. I mean, it has been known that in higher dimensional gravity, asymptotically flat, there are certain instabilities of black holes without certain fine-tuning apart from critical collapse. I mean, there's an open set of initial data, but that probably leads, or numerical simulations strongly suggest that there will be solutions that could that lead to a topology change of black holes. For example, the black string is known that it's subtle to Gregory Flam type instabilities, and numerical simulations strongly suggest that also actually what will happen in the long run, that these solutions will actually pinch off. And referring to this other work, so the ideas or the claim that in this paper we made, I mean, it's not a full GR, it's not full GR dynamics, it's just done in a larger D expansion. And so the claim in this paper is actually that you don't need to go to initial data like resembling black brains or something. So in this case, it's just colliding black holes, and the idea was, the physical picture we wanted to present is that you can collide black holes, will form an object if you get into and that you can get into an unstable regime, and these objects that will form will be subtle, or it will be susceptible to actually pinch down and evaporate, at least in a strong regime. So then, of course, the question is, how do you want to describe these this pinch off, or what actually happens there? I mean, there you probably would have to give some input how this actual pinch down will happen, and how this is also how this would be framed in terms of classical gravity, and how susceptible, or how the classical evolution can be continued after this is also, I think, an interesting question.
So I want to respond to what Gerard said. We know that if the system has a finite entropy, by your argument, you cannot have a true horizon, right? Because the entropy, if the redshift would be infinite, the entropy would be infinite. So something can and needs to get out. And in fact, I share the feeling or the idea that the key is resolving the singularity, because the current indications that I see is that resolution involves horizon scale modifications. And that makes it interesting both theoretically and also observationally, because if you have horizon scale modifications in the structure of black holes and you take them out of equilibrium, you can excite some of these issues. Now, it's true that, for example, what you do, if you integrate out whatever resolves the singularity, you can forget about the interior, as you do in your scattering problems. But it's only valid for a certain setup. So, for example, if you imagine that you excite the black hole with finite entropy, the integration out procedure that you did to get your S matrix would no longer be valid. So it's true that if you know what the resolution is and you can integrate it out and describe the exterior in a good way, then you can ignore the singularity. But if you want to describe the state of the black hole, I don't think that you can do
that. No, there's always been the question whether a black hole is stochastic or has irresolvable, sort of stochastic behavior, or whether it's regular behavior. Now, that all depends on how you approach the physics. So, for instance, an ideal gas, is that chaotic or regular? You could say that every atom, if you have a cubic box of a real gas, you can say every atom behaves in a well-defined way. So it's not chaotic. But then, of course, if you start with 10 to the 26 atoms or molecules in a gas, very soon you can't follow how they all behave. So it looks chaotic. I have the same situation in black holes. If I make my spherical harmonic expansion, for every single spherical mode, their behavior is completely regular. But if you add them all up, you get a system which is chaotic in the same sense as an ideal gas is. So it starts to scatter against the walls and...
the chaos in the black hole is just a manifestation of strong coupling
No, that I'm claiming is not. The strong coupling goes away. I mean, what? Well, no, it was modified. It replaced by a boundary condition. Things that go in to a horizon come out Fourier transformed out of the past event horizon.
Yes.
And
is that I agree, but still,
really,
if you want
chaotic or something, that is just a well-defined physical law. Of course, like all laws of physics, if you combine them all together, you get chaos. I mean, a neutron star is a very interesting object, but I don't expect any regular behavior inside a neutron star.
Yes, but
so I think eventually a black hole will be very similar. But you can still try to resolve things at small scales. The small time scales or small position scales or small regions on the horizon. There you hope still to find regular behavior. Even in an ideal gas, that's the case. I mean, in an ideal gas, the collisions are relatively rare. Or if the gas is really ideal, they don't collide at all. And so the laws of physics for one molecule during one collision at a wall is totally regular. And this is, of course, the way we want to investigate physics. I want to investigate black holes from this perspective, that at short time scales and with few time scales short compared to the black hole mass in natural units, the behavior is completely irregular. But at very long time scales, it is as irregular as anything else in the macroscopic world. Planetary system, planets are very irregular at a scale of a couple of years, but at a scale of a million years, they are chaotic and irregular. And so that holds in many branches of physics, including black holes.
Yeah, so there is a apparent difference. It seems that there is a difference between an ideal gas and black holes. Ideal gas are weakly coupled. So, in black holes, there are many.
The different angular mode, LM modes, are all very weakly coupled.
But let me just make the point, okay? So, ideal gas is weakly coupled, and so in that sense, this is the regularity that you were talking about. With black holes, there are many indications that they are not the degrees of freedom, whatever the degrees of freedom, they are not weakly coupled. The chaos, for example, is one of these indications. It's just a ratio of the quantum wavelengths.
Well, some people think they have these indications. I don't. I see just weak coupling, like happens in so many branches of physics. There's weak coupling, which gives, at a long time scale, it gives complete chaos. But at very short time scales,
yeah. This seems to be different. We can discuss that after. There seems to be a real difference in this case.
I don't agree. I mean, it's all gradual. I mean, some things are more chaotic than others, sure.
And I said, probably you can integrate out the interior and then have a scattering matrix that is similar to what you were describing. That I think is correct. But if you want to describe other phenomena that are associated with the black hole, then you need other tools.
Unless someone else wants to jump into this, I think this is something that the two of you should save for after.
Maybe I could just say a word too. Which just kind of my general feeling regarding it is that, like, if you start with, say, like an internal black hole, and you do field theory on this eternal black hole background, then kind of at that level, like, there's no question you're going to get information loss. It's going to look pretty regular. I mean, as you say, it's just weakly coupled field theory at the horizon. It's going to be totally behavior we'd characterize as totally normal on grounds of just what we know about effective field theory on regions of low curvature. But yeah, then information is lost. Just the causal structure is such that you can only go into the horizon. But so then now you can start playing that game of saying, okay, well, how am I going to change this effective? I'm going to make some small modifications.
Doing something else.
Something else? Totally? No? Okay.
As far as I can see, the information is only lost in the same sense as an ideal gas. So yes, an ideal gas at long time scales is completely chaotic, but at short time scales, there's no reason to expect strange kinds of chaos.
Okay, I guess I won't add anything else then.
Other comments or questions?
Oh, actually. But on a different topic, which is just to come back to this business about resolving singularities and how that might help us with the black hole, how in understanding how information gets back outside of the black hole, which is to maybe what I propose is to give you an example of one purported way in which this might work. And so, okay, let me paint for you my very crude understanding of how fuzzballs and the fuzzball picture is supposed to work. So if anyone's like an expert on fuzzballs, or, well, even just like a string theorist, which I am not, feel free to correct me. But my very basic understanding of fuzzballs, how you'd address the information problem in this case is you'd say, okay, well, let's suppose we live in 6 dimensions, or however many dimensions you need in order to write down these fuzzy geometries. In this case, there is no horizon. There's just some very complicated geometry behind, maybe some superposition of geometries. I don't know, but there is no horizon. So anything that goes into the black hole, including the matter that's collapsing to form this black hole, you never go behind a horizon. There's no Hawking radiation in the sense that you have a horizon separating two regions of space, ingoing modes, outgoing modes. No, you just have stuff that then goes into, and now this is my extremely crude picture, essentially a very complicated diffraction grating. It just spins around, gets ripped up, does its thing inside this fuzzy geometry, and then eventually just comes out again. And so it may be a very, very complicated S matrix, but in principle, this is one way you could imagine resolving the information puzzle. Just say, well, okay, there is no horizon. It just stuff goes in and gets churned around in a very complicated space with extremely complicated topology. So, anyways.
Further response or comments? Is that a yes?
Say the obvious, which is just, well, I can say what people typically say, which is just that you're breaking, now the horizon's a special place, and so you're breaking, I guess, diffeomorphism invariance, or you don't want you're breaking the equivalence principle, so you would like nothing special to happen at the horizon.
There is no horizon. This is just it's like a geometry that caps off. Very high.
You're breaking GR at the low energy scale, and that seems.
Oh yes, I mean it's definitely, yeah. Which is why I think fuzzballs. Again, please, someone who knows about string theory, please step in. But I think this is why, like, generally fuzzballs seem to run into trouble when you try to do it in, say, a 3+1 space-time. So, I mean, you run into things like, well, okay, we think black holes are not supposed to have air, and you're claiming that no, there's actually like this huge collection of geometries that are consistent with data outside where we put a black hole. Did everyone hear? I can. Okay. That's yours now. It's mine now.
Well, other response?
So thinking in terms of this Mallas picture, where the 2-point function, whether at late times it shows exponentially decaying behavior or Poincare recurrences. So I think in terms of this doing some quantum gravity path integral, as soon as then I have some horizon structure, I will have this behavior, right? That was the idea. So if I have a geometry like fuzzball and no other geometries with horizon in it, then it will work.
Okay, well, maybe directing back to the question I asked before. So let me rephrase it. If we're looking for a theory of gravity within quantum mechanics, showing some prejudice of how to think about it, what should we be doing? Or what are the questions we should be going after next?
I can give a self-serving answer because I've just written a paper. So I think one thing that would be interesting is taking understanding the classical limit of quantum gravity. So, and at the moment, previously the only thing we really had was the semi-classical Einstein's equation. We know that's inconsistent. If I have a superposition of a planet in two places, or a statistical mixture of a planet in two places, then if we use the semi-classical Einstein equation, we get crazy things like a planet should be attracted to the place where it might have been. Sorry? Yes, I believe that. I mean, so I do believe that. But I was, but Steve wanted us. Yeah, so the theory I have is that it's a classical theory of gravity, but I want to take I don't expect people to believe that. So taking Steve's question, it's still the theory we have is still a classical limit of quantum gravity. So if you want to take the classical limit of just the geometric part, then at the moment the only tool we have is the semi-classical Einstein's equation, which is pathological. But in quantum information theory, we know how to deal with those kinds of linearities. We know how to deal with taking the classical limit of just one part of our system and still getting a consistent theory. You don't take expectation values, you use a master equation, like a Lindblad kind of equation, and then you don't have any non-linearities at all. So I feel like I feel like people in quantum gravity are not so aware of the master equation picture. And that is a consistent way to take the classical limit of quantum gravity. And it means that you don't have these kind of pathologies that, mixtures get attracted to the place where they would have been, or, you take expectation values and so test particles go down the center. And so I think it'd be worthwhile to look at a lot of the previous calculations of, say, black hole evaporation or inflation, where you're trying to do the back reaction, and look at a master equation where you can actually have a consistent, it's a consistent way to do the semi-classical limit. And people often say, well, we can use a semi-classical Einstein's equation in the case where the fluctuations are small, but that's almost like saying, and people get angry if I say this, but that's almost like saying we can only use the semi-classical Einstein's equation when it's irrelevant, which I think is true. And so I feel like, well, if fluctuations are big, then if I have a 50% chance of two things happening, the semi-classical Einstein's equations tell you, that those things attract each other, and they are like.
That's okay, but the other part I didn't. We don't only use it when it's irrelevant. What about the evaporation of a black hole?
Right, I'm just saying, when it's relevant, when you have large fluctuations, then it's giving you answers that don't make sense. And when fluctuations are small, then okay, you can use it, but it's not that interesting. And when you use it in black hole
evaporation isn't interesting.
Yeah, in black hole evaporation, you're kind of cheat. You might be able to extract some information from it, but you're almost cheating. You're effectively, if I have a planet that's on the left or the right, the semi-classical Einstein's equation tells me those things attract each other, and I go down the center. I could kind of cheat and say, well, really, some of the time it's on the right, and then I'm going to use Einstein's equations. That's something you could do to try and get some information from it. All I'm saying is the master equation approach that we're looking at is a way to do it consistently, and I think it's worthwhile looking at such things.
Since you think it's worthwhile and thought it was worth telling us about it, could you, instead of just referring to the name master equation, tell us what the key physical idea is that resolves the issue of large fluctuations?
Yeah, you can. Is this working? So I guess people that have done a little bit of quantum information, you're probably familiar with thinking about, I have a density matrix, and I want to know what allowed physical operations can happen to the density matrix. So it has to be completely positive, it has to be linear, and it has to be trace preserving. And so you can ask what kinds of dynamics do that. And the semi-classical Einstein's equation doesn't do that. It's not linear, for example. But you can ask what's the most general dynamics which do that, and you get an equation. In pure quantum mechanics, that equation looks like the Lindblad, that's called the Lindblad equation.
You're telling me about general formalism, but on the gravity side, you told us if you have a superposition of a planet here and a planet there, the semi-classical equation tells you that something falls to the mean value, which is stupid. So you have a better answer. What's your better answer?
Better answer is that it goes to the right or to the left, depending on whether the planet is on the left or the right. if I were to, you're getting a wrong answer because you're in some sense tracing out degrees of freedom and reconstructing the equations for the phase space. What you should be doing is looking at the evolution equation of the density matrix.
Density matrix of which degrees of freedom?
Of both the matter and of the geometry.
Tracing out what?
Well, you don't need to trace out. You're just taking the classical limit. So what I'm saying is, when people do the semi-classical Einstein equation, they just take this this classical equation. Imagine one side is just an expectation value, and that's going to give you nonsense. What you should do is take is look at the density matrix of your theory, which is just, in a classical theory, it's just a phase space density.
One second, can I just ask one more clarifying question? So I think what you're saying is something that could apply to all kinds of quantum systems, not just gravity or anything. So are you saying that in a situation where a quantum system would lead to macroscopic superpositions, if you just look at the density matrix of all variables involved in the system, it will evolve in the way you're saying, such that because of internal decoherence of the system or something like that, it will naturally focus onto the reasonable trajectories where different alternatives are correlated as they should be within the wave, as the wave function says they should be. Is that what you're saying, basically? I mean, because we could imagine a simple non-gravitational system that behaves exactly the way you're talking about. What would the answer be?
Yes, sir. The easiest one is take the Stern-Gerlach. Just I have a spin particle. If it's spin up, it'll go one way. If it's spin down, it'll go the other way, and I can solve that quantum mechanically. And now, take the classical limit of that. Sorry. Well, I can decohere in the, I can decohere the thing.
For that particular problem, there is no that's the whole point, right?
No. If you look, so let's imagine just tracing out the spin. Okay. Trace out the spin, and ask how does the center of mass behave. What would your answer be? Well, you'll actually find that the center of mass goes down the center. Right? If you take the Heisenberg equations of motion and trace out the spin and just say, what does the center of mass do? It goes down the center, and you say, that makes no sense. Why, I know it doesn't go down the center. And that's because you're tracing something out and looking at the expectation value of the center of mass of the particle. And yes, the particle sometimes goes to the left, sometimes goes to the right. If you take the expectation value of that path is down the center. And so if you do the semi-classical thing, you'll get confused. But if you do it as a master equation, you won't get confused. So I'm just saying the same confusion that plagues the semi-classical Einstein equation, you can just see from the a Stern-Gerlach where you can fully quantize it. That's that's the wrong thing to do, but looking at the master equation gives you something sensible and gives you the right classical limit. Is that?
I'm sure Jonathan would be willing to give a mini seminar afterwards to anyone who is interested.
That's standard quantum mechanics.
It's standard quantum mechanics, and exactly. Well, no, but exactly. But you know that the wrong thing. You know the wrong thing to do to take that.
If you do wrong things, you get wrong answers. But you are describing standard quantum mechanics, right?
Exactly. So I'm just saying, why would we? If we know in the Stern-Gerlach how to do it properly, why on earth? And we know that it's wrong to trace out something and expect anything different. Why on earth, when we do the semi-classical Einstein, are we doing this thing we know is wrong?
We usually do it in stupid places.
Yeah, we do places where we think we can kind of already know the answer.
Okay, let's continue this. So Jonathan's answer is, the way I phrased the question is bad. We should not look for gravity within quantum mechanics. We should do something else, which, and he can try to explain that further. Other possible responses or comments?
About that or about anything?
Either.
Maybe in response to that, just to, is it fair to say that morally this that morally the approach, like when you're doing the master equation, is so. Okay, let's suppose we were trying to do some semi-classical gravity and saying that okay, instead of tracking the expectation value of the stress energy tensor and saying that this is the thing that sources the Einstein equations, I'm going to track several configurations for the stress energy tensor and track how their probabilities evolve over time. And then at the end of the day, you have a prediction for some probability distribution over a set of configurations, which might be classical. Of course, you could then sum them all together and say, oh, and then the total expectation value is blah. So it can be like, just an analogy with the Stern-Gerlach saying that, well, okay, I could either track the average values of the center of mass position, in which case, yeah, indeed, you would find it just sails on through the middle of the apparatus. Or I could say, okay, I'm going to track the probabilities for my two configurations are going to be the thing went up and the thing went down. I have a prediction for how those probabilities evolve over time according to some master equation. And of course, I could just take them and sum them up together at the end of the day, and it would be the expectation value for the center of mass position and just 0. Yes? No? Unclear?
I feel like I had a self-serving answer. I feel like Steve...
We've raised the topic.
Okay.
You asked a question. I'm happy to answer after, but I don't want to derail this discussion on
okay.
It's,
okay.
You don't have to.
Let's say.
I just want to clarify. I'm not saying. I believe I'm answering the question honestly in the sense that I'm just saying. I think we have a better way of taking the. Imagine that there is a quantum theory of gravity. I believe we have a better way of taking the classical limit. That's what I'm not saying.
Yeah.
Please trust my crazy theory. I'm just saying we know how to take the classical limit in a better way than using the semi-classical Einstein's equation, which is, to imagine to take the Heisenberg equations of motion and then decohere the classical Hamiltonian.
Yeah.
And that will give you a master equation, and that's the way to take the classical.
Yeah, I mean, for what it's worth, I'm actually very happy. I'm just making sure I'm not happy for the wrong reasons. So.
Okay. Comments in other directions? Or we could, close to time to wrap up, but again, I want to allow any opportunity to raise thoughts, or no one has really answered my question. What are the important questions to answer next? But I'm sure you all have your own ideas, and we'll put them out in your next papers. But if you want to share any, anyway, okay. So, no other thoughts or comments? Okay. Well, I see no harm in wrapping up just a little bit early. I do want to say, thanks to everyone who came. This has been a really lively and exciting and interesting meeting, and it's been a lot of fun. So thanks, everyone, and for all your contributions. And I wish you all good travels. So,
thank you.
Okay.
Can we thank the organizers?